Hello everyone, very good morning. I'm Jyothi Shetty from Computer Science and Engineering Department, RV College of Engineering, Bangalore. So at our university, we have a Center of Excellence that is established in association with HPCC Systems. At this Center of Excellence, we carry on a lot of activities such as project presentations, hackathons, paper presentations, internships, and workshops, seminars, etc. This Center of Excellence is named as RVC HPCC Systems, Cognitive Intelligence Systems for Computing Solutions. And this HPCC Systems mentors, experts support all of these activities. So today I'm here to present one such project that was carried out during the academic year 2022-2023. This project is titled as Building Scalable and Efficient Bitcoin Blockchain Parser on HPCC Systems platform. This is a work in progress in the sense we have successfully implemented this project and it works on hThor and it requires a little bit of adaptation and modification for it to work on Thor of HPCC Systems. This project was carried out by students pursuing their second year graduation in Computer Science and Engineering at RVCE. And they are Ms. Anagha Anand, Mr. Chandan Kasamasatti, and Mr. Harsha HL. The faculty coordinators of this project include Dr. Shobhaji, a professor and lead Center of Excellence, and myself, Jyothi Shetty. And this project was mentored by Hugo Watanuki, manager, Community Tech Program, LexisNexis Risk Solutions. So this is the outline of my presentation. So I'll begin with introduction to Bitcoin, system architecture, methodology, demo, and then results and conclusion. So to begin with the introduction to Bitcoin, Bitcoin is a pioneering cryptocurrency that was created in 2009 by Satoshi Nakamoto. Satoshi Nakamoto says banks must be trusted to hold our money and transfer it electronically, but they lend it out in waves of credit bubbles with a barely fraction in reserve. This centralization of banking and the resulting financial crisis of 2009 inspired Satoshi Nakamoto to develop the Bitcoin system. The Bitcoin system was created as a solution to centralized modern banking system, where we have a small number of large banks and they completely control our money. They decide who can create an account, what transactions get processed, etc. These banks have complete control of our money, and we have no other option but to trust these banks to act responsibly. So Bitcoin is an electronic payment system, and it allows you to send money to anyone in the world, and you don't need anyone's permission to create an account. It can be used by anyone and to run the program, and anyone can use the system. So Bitcoin, it's based on a blockchain technology. So blockchain, it's a public, decentralized, immutable ledger for all transactions. In blockchain, the transactions are grouped in blocks, and the block is added to the chain of blocks, and these blocks are very secure. They use a strong cryptographic system, and no one can alter or tamper these blocks. Thus, this blockchain system, it serves as a robust, secure, transparent system, and there is no single point of control, and it acts as a very good platforms for these cryptocurrencies or for electronic payment system. So what's a Bitcoin blockchain parser? So the parser is basically a program that is used to extract information from the blockchain and make it available in a usable format. So what is the use of blockchain parser? It is useful in understanding and analyzing the vast amount of data that is stored on blockchain. It facilitates data analysis tasks, helping the researchers and developers, analysts to make informed decisions. There are various practical applications of this blockchain, and they include forensic analysis, where it assists the law enforcement agencies in tracking illegal activities and investigating criminal transactions. It helps in transaction monitoring, where the financial institutions can use it to identify potential risk and ensure compliance with regulations. It helps research and academia as an invaluable tool for studying the behavior and economics of cryptocurrencies. So what's the role of HPC systems associated with Bitcoin? In case of Bitcoin, a new block is formed approximately every 10 minutes and is added to the existing block. And clearly, the volume of data is growing with the time. And due to this large volume of data, the process of analyzing transaction becomes a challenge. And here comes the distributed and parallelized architecture, such as HPCC systems, as a solution to efficiently analyze such huge amount of data. HPCC Systems with ECL programming language offers open source data lake platform that exhibits rapid scalability as the data volume increases. This project proposes a C++-based Bitcoin parsing algorithm that is embedded within ECL to create a robust and efficient blockchain parser. The parser that we have implemented, it basically takes a raw blockchain data in the form of a .dat files as input and processes the headers and transaction data of the block. Further, it maps the input addresses to the output addresses. Addresses to the output address of previous transaction, constructing a network of blocks, and it iterates these chain of blocks and passes the contents to write it to a CSV file. The suggested the project that we have implemented is flexible in terms of that it does not rely on any of the external library and can be executed as a single file. Thus, as the size of blockchain data continues to grow, having a scalable and reliable ECL Bitcoin parser that enables retrieval of blockchain data with a minimal overhead is going to be quite beneficial for the society. So in order to implement this blockchain parser, the very first step was to understand the block structure. So here on the screen, we see the Bitcoin block structure. The Bitcoin block structure, it starts with a magic byte, 4 bytes magic byte. It's a unique pattern or unique string that identifies the beginning of the block. Magic byte is followed by 4 bytes of size. Size stores the block of the size of the block, and then it is followed by block header, which stores the metadata of the block, and it contains version, previous block hash. Previous block hash basically stores the hash of the previous block, that is the block that precedes this. Thus, this field acts as a chain or a connectivity between the previous block and current block. And then we have a Merkle root. Merkle root basically is a hash of all the transaction hashes in the block. Time represents the unique timestamp when this block was created. And then we have bits and nonce, which we'll see later. The block header is followed by transaction count, which stores the number of transactions that are there in this particular block. The transaction count is followed by transaction data, which forms a major part of the block. And this is the structure of a transaction block, wherein we have a version and input count. Input count represents the number of input addresses that are participating in the transaction. And then we have an input. Input is associated with the transaction ID, vout, and script signature. We have an output count. Output count represents the number of output addresses that are participating in the transaction. And then each output is associated with a value, which represents the amount of Bitcoin that has been transacted. It's also called as a Satoshis. And then we have a public script, public key, and then log time. So after understanding this block structure, the next step was to look into the actual Bitcoin data. For that, we retrieved the raw data from the Bitcoin, and the hexdump of that data looks something like on the screen. So what we did is we tried to map the block structure to this data, and we analyzed that the first 4 bytes should be representing the magic number, the next 4 bytes should be representing the size, and so on. In order to confirm with what we are assuming or analyzing is correct, we verified this with an online site called Bitcoin Blockchain Explorer. So this is a site wherein if we give the block number or any other information with respect to the block, it gives the details of the block. So what we did is we gave the block number as an input to the Blockchain Explorer, and we compared the value that is there in this hex with the one that is seen on the screen. Say, for example, here size is 732, and it represented it was matching with the size value that is present here, thus validating our understanding. So with this, our next step was to extract this this data from the hex and put it into the CSV file. So for that purpose, we came up with this system architecture. So in this, we have a Bitcoin core node running. We retrieve the raw Bitcoin blockchain data files. These data files are available in the form of a .dat files. And once we obtain the raw data, we spread it or distribute it onto the HPCC systems. And once the data is distributed onto the system, we can use the ECL string handling functions to parse the content and write them to the CSV file. Thus, the CSV file can be used for further analysis. The next step is to implement and test the parser on the live transaction. So this is the system architecture that we came up with. Going into details of the methodology. So the detailed process of extraction of the Bitcoin data. So each of the .dat file or the .dat file has got information about multiple blocks of on the blockchain. So the very first step is to get the extract the block from the .dat file. Once we extract the block, we extract the block header. The block header contains the metadata of the file. Then we determine the number of transactions in the we determine the number of transactions or extract the number of transactions and write it to the CSV file. Similarly, we determine the number of input and output addresses. And the last is we destructure the input and output addresses. That is basically we extract the list of input and output addresses. Going ahead, the algorithm for retrieving the block from the .dat file is something like this. So we determine the length of the blk file. We set the offset to 0. And then until the end of the block, we compare the first 4 bytes of the data with the magic byte. If it is matching, then it represents that this is the beginning of the block. So if you recall, following the magic byte is the size field, which stores the size of the block. We advance the offset by 4. We retrieve the size of the block. And then we advance the offset to point to the start of the next block. And then we return the block, which is from offset minus size to offset. So in this way, we retrieve the block from the .dat file. So the header, the block, block header, it is basically which contains the metadata. It is from 0 to 80 bytes. So after extracting the block, we extract the block header and the other details that are stored in the block header, and we return the block header. The next step is to calculate the number of transactions. So following the header block is the transaction block, so which starts from 88 byte till the end. The transaction count field in the block header, it's a variable size field. That means that the size of that particular field may vary from block to block. So for that purpose, we use a decode variant function here. So this decode variant function, it determines the size of the field and extract the information accordingly. So this decode variant function, it takes the transaction data and it returns the number of transactions and the offset. And after determining the number of transactions, we here are extracting the transaction. We are returning that particular transaction, basically writing the transaction to the CSV file, and then we are advancing the offset. Then to determine the number of input addresses in the block, we the number of input addresses is a variable sized field. So we use the same decode variant function. We pass the transaction data, which returns the number of inputs and the variant size, the size of the input. So same is applicable for the number of outputs field. So after determining the number of transactions and the number of input and output addresses, the last step is to determine or extract the addresses. So for that, we initialize the list to empty, and we iterate from I from 1 to the number of inputs. We retrieve the address, first address, and then we advance the offset to point to the next input, and we append the extracted address to this empty list. So we do this until we retrieve all the input addresses and we append it to the list. So the same is applicable for getting the list of output addresses. So this is the detailed algorithm for retrieving the data from the raw.blk.dat files and writing it to the CSV. Now let's move on to the interesting part of the presentation, and that is the demonstration. So what you see on the screen is the GitHub code where the source code for the Bitcoin blockchain parser using ECL is stored. So here we have the source code, the instructions on how to execute it, the description of the output, sample input files, and the software that is required. All the information is available in this particular GitHub. So the work that we have done, it's an adaptation of work done by Jeff Chan. Jeff Chan has implemented the Bitcoin blockchain parser in C++, and we have extended this work by embedding it in ECL and making further adaptations such that it works on HPCC systems. And in order to execute this particular program, we need software that is HPCC system cluster. So the cluster should be up and running. It can be either a remote cluster or it can run on your local node. And on your local node, you need to download and install ECL client tools. And you can either use ECL ID or VS Code with ECL extension. Once you have these softwares in place, the next step is to upload the raw Bitcoin blockchain data onto the cluster. So here we have made available sample 2 input files, which you can download and use it, or else you can use any .dat files if you have. So I'll show you to upload this onto the cluster, how to upload this onto the cluster. So here we were in the process of distributing the .dat files onto the cluster. You can select the cluster. You can select these .dat files and select the blob option to distribute on the cluster. And once you click on spray option, the files will be available as a single logical file. It will be available as a single logical file here. As you can see, this is the logical file. And if you note down here, you just click on this particular file and it will open the properties page for you. And here you can see the properties of the file. And one information to note down here is the path, the directory path where the logical file is available. This is required for our next step. So now, once we have uploaded the data file onto the cluster and distributed the data, the next step is to go ahead and source the ECL code and execute it. So the ECL code is available on the GitHub as a parser.ecl. So you can download this particular code and paste it in your ECL IDE. And there are just 2 changes that you need to include in this particular source code. And that appears at the end of the file. So here, the 2 changes that you need to do to this particular program is the input file path and the output file path. So the input file path, which represents the logical file, is to be given here, which we have just noted in the previous step. So you need to provide that path here. And the output path is the path of the CSV file where the parsed data is to be written. So here you can observe this is the path to my drop zone. My drop zone is basically the landing zone where we had uploaded the data file. So the program is going to parse the content and write to the CSV file, which will be available on the landing zone. Or in order to save the time, I've already executed this particular program and it's available on the cluster. Yeah, so you can see this particular code has already been compiled, executed, and completed. Going to the ECL code of this particular work unit. So here I'm going to note down the output file path. So you can see the output path is varlib HPC Systems my drop zone parser output.csv. So I'll go to the landing zone and look for this particular file. So here it is, parser output.csv. We can select this and download this particular file. And once this is available, I'm going to open this. So here is here is our output file. To note down the output, it has got the computed block hash. Computed block hash is basically the hash of the current block, and previous block hash is the hash of the block that precedes this. Here in this case, it is 0, because if you have noticed, we have used blk.dat file, which was the very first block on the blockchain network. And this is called as a genesis block. And as this was the first block, there's no previous block to this. And then we have the next block, which is the hash of the block that follows this particular block. We have the Merkle root, which we already discussed. It's a hash of all the transaction hashes. The time when this particular block was created. And nonce is a unique integer value that is added to the block in order to create a unique hash value. And this nonce is also used by the Bitcoin miners for mining the block. And then we have a block reward, which is the reward that the miner gets once he mines the block. So then during the initial Bitcoin blockchain mining, it was 50, and it is reducing year on year. Currently, it is around 6.15 or 6.75. And block reward is followed by transaction hash, which represents the hash of the particular transaction, and then the input address. So input address here is blank in this case because it's a Bitcoin, it's a coin-based transaction. It's a transaction in which the mining was done. If not, it will represent the from address or the address from which the transaction is done. And this is a multi-valued address wherein it can have multiple input addresses. And then we have our transaction hash of the inputs. And then we have the input amount, basically the amount of the input. And then we have output address and output amount. This transaction being the coin-based transaction, here you can see the output amount is 50, which is nothing but the block reward. So we can see some of the examples wherein we have input addresses also. So you can see here, this is an input address. This address represents from which the transaction was done. And the amount that was transacted is 10 and 40 Bitcoins. So in order to validate this particular input, we again use the online blockchain parser. Blockchain Explorer, and we gave the block information to this, and we verified the content that was mined, verified the content of the CSV file. We verified the content of the CSV file using this blockchain explorer, and and we found that it mapped accurately. So this data which we saw on the blockchain explorer was mapping with the one on the CSV file that we have parsed. So in this way, we validated the output that we generated. So coming to the results and conclusion, using the distributed and parallelized architecture of HPCC systems has substantially increased the parser throughput, and it is also scalable in that as the Bitcoin network and other cryptocurrencies continue to expand, the parser can easily adapt to the larger data sets, and also it results in a swift data retrieval. The future scope is to use the parsed output to implement AI-based illegal transaction detection, and we can use that parsed CSV file for performing the real-time analysis. And right now, the work that we have done is for a Bitcoin cryptocurrency. It can be extended to other cryptocurrencies as well with a minor modification. And also, the work is to be extended to successfully execute on the Thor cluster. So these are some of the papers that we have referred. Thank you one and all for your patience listening, and I thank RBCE and HPCC Systems for providing this opportunity. And now my colleague, Professor Manonmani, will be continuing to discuss her project. Thank you one and all.
Hello everyone, a good day. I am S. Manonmani, working as Assistant Professor, Computer Science and Engineering Department, RV College of Engineering, Bangalore, India. Along with me, I have Sudershan, RVCE student, third year student. Both myself and Sudarshan both are going to discuss about the technical overview of the topic entitled as Performance Optimization of Learning Tree Modules in the ECL repository. So we have submitted this proposal to HPCC Systems, LexisNexis risk solution. Then we got approval. Then after last 8 months, we were working on this project and we got some promisable result, that performance optimization of learning tree modules in the ECL repository. So two students, Sudarshan, third year students, and Sashank B, second year students, both the students, they involved in this project. Then mentor from RBCE, myself and Dr. Shobhaji, and from HPCC, LexisNexis, from the mentor is Mr. Roger, LexisNexis risk solution. He has given a lot of inputs during our journey. So this proposal is generally in this speaking proposal category, HPCC Submit 2023, that we are going to give the detailed description, whatever we have done with last 8 months. We are going to present the technical overview, what we have done during these 8 months. This HPCC systems. So HPCC system, it's a open source platform. It's a powerful big data management platform. So provide end-to-end solution to data lake management solution. So advantages of using HPCC systems is the scalability and performance and usability. So alternative to existing database, that is a big data platform such as Apache Hadoop and Apache Spark. So along with this, HPCC systems, it is supported its underlying programming language called ECL, that is Enterprise Control Language. So which implicitly provide parallel and declarative in nature. So provide several parallel constructs. It simplify the parallel computing task. So need for multi-node computation. So why we need for multi-node computation? To enhance performance by distributing tasks across multiple interconnected nodes. Scalability is the key advantages of multiple multi-node setups, allowing easy expansion of resources. Fault tolerance is also improved. So complex simulation, data analysis, and AML training benefits from the parallel processing power of multi-node clusters. So efficient resource utilization. So here we are minimizing the wasted computing power and energy consumption. Also it is there. If we effective load balancing, we can utilize. So here in this HPCC systems, machine learning libraries, we have ML core libraries. So extensible collection of machine learning routines. So we can use these effectively to do ML based applications. So here we have machine learning routines such as associations, classification and clustering and correlations. So these kind of machine learning libraries such as ML.associate, ML.classify, ML.clusters, ML.correlate, these kind of libraries, it's a powerful libraries. So you can make use of cluster to improve the performance. So already in ML core libraries, they have decision tree. That is, in HPCC, we call it as learning tree. Learning tree is referred to as, that is, decision tree is nothing but learning tree in HPCC platform. So learning tree bundle, it provides an efficient, scalable implementation of learning tree methods in HPCC systems. So in that current machine learning bundle, it provides decision tree, random forest, gradient boosted trees, and boosted forest algorithms. So here we can use numeric data such as real values, integers, binary, and categorical data. Output can be categorical for classification forest, and regression forest, it is real valued. So this is tree-based algorithm. This is tree-based algorithm. So decision tree-based algorithm. Then decision tree has been used since 1930. It is a way to structure knowledge using a cascading set of rules. So advantages of using this decision tree, that learning trees provide their that is flexibility in learning. So we need larger amount of data to get strong predictions. So in ECL, we have loop function. In normal machine learning, that is learning tree bundle, they have used loop function. Then this is not like normal loop function. It is like a recursive in nature. So recursion is used when a problem is too complex to write an iterative code. This will take normally that large amount of data while processing large amount of data. So what will happen? It will take a lot of time. Our proposed work, what we have done, we have used embed function in the already existing library, the decision tree, that is learning tree bundle. Learning tree, we have used embed function. We have embedded Python libraries in ECL code. Then after that, we have used several data set like Irish data set, and one more data set is for regression tree analysis as well as classification tree. We have used two different data set, and we have executed our proposed model in single node cluster as well as multi-node cluster. Then we got runtime. Then we identified, then we computed that runtime. We got very good result that runtime is got reduced. So we have that comparative studies, that result and analysis we will discuss later. Then now demo will be given by Sudershan. Sudershan, you can take over this session.
Hello guys, good morning. I am Sudershan, a student of RVCE Bangalore, and I'm going to explain the technical aspects of our project, that is performance optimization of the learning trees bundled in ECL using Python. So here, has my teacher Manonmani explained the basic introduction to a project. Let's look into why actually we thought this would be a good idea to implement. If you look at the advantages of embedding a procedural language into ECL, the first and the primary advantage is that it enhances the functionality because they are data-centric in nature. It provides advanced algorithmic capabilities that you might need to improve existing algorithms and also for efficient utilization. Secondly, you also have efficient data processing because they support data manipulation and improving performance in data-centric tasks. And there's also an added advantage of customization when you use procedural language like Python, which are heavily user-dependent. They also give way for parallel processing to increase the computational speeds, because every second that the algorithm takes to execute is counted in terms of cost, and we plan to reduce costs as much as possible. And lastly, performance optimization, while keeping speed and efficiency has our centered performance criteria, we also try to maintain the accuracy of our predictions. So now let us look ahead to what specifically we did. Now we have to give a brief overview of the embed structure. It looks something like this. So embed is basically a call from ECL to shift to any other language that you are possibly trying to embed into ECL to use the functionalities and the libraries of the other language. It could be Python, C, C++, Java, Ruby. There are many procedural languages that are supported by ECL. Now here, we primarily look for Python. That is where we've executed most of our results. And the embed structure goes something like this. You have the result type, which is the type of the result that would be returned once the embed is ended. You have the function name. That is the name of the function you want to call in the procedural language that you're embedding. The parameter list, that is the data from the ECL that you're passing into the embed, which in our case was a set of data sets, the independence list, the dependence lists. and once the code, which is specific to your language that you want to embed. And once you end embed, you come back to the ECL along with the return result. Now, we have made use of scikit-learn libraries, which is a very proficient and powerful library in Python, which is very widely used for machine learning and AI-based purposes. And two major functions of that library we have made use of are decision tree classifier for classification datasets and decision tree regressors for regression datasets. And we have used a concept of multi-threading, which is an operating systems concept to be general, but we have implemented that in Python to improve our efficiency and also provide more freedom and leverage to the user to control how the execution takes place. Now we'll go ahead to see what the general proposed model looks like. So on the everything on the green blocks is the ECL side, and whatever is being done inside the blue box is what we have done inside the embed function. Now we start off by importing the dataset. As I mentioned, the dataset could be regressive in nature, which is basically numerical data, and the output is also a float or an integer. Or it could also be a classification data where you're trying to predict what category the output will belong to based on the given data set. We do basic pre-processing like labeling the data, converting them into numerical fields. In case of classification, we encode the labels, and then we have spraying data onto the multiple nodes that we are using. In case we are doing it on a multi-node cluster, the given project can also be executed on a single node cluster, in which case spraying of data is not necessary. Next, we create necessary lists for results. That is, we create input lists, the result in which the output will be stored, the result in which the predictions will be stored, and also the model which will evaluate the result. And lastly, we take the user input. In case we are using multiple decision trees in terms of a random forest, we also give user the flexibility to decide how many number of trees he wants in the random forest to make the prediction. And once we go, then we call the embed function and go to the Python side. In the Python side, depending on classification and regression, more or less we follow the same procedure until we reach the stage where we call the prediction, where we use decision tree classifier or decision tree regressor accordingly. So first we have to import necessary scikit-learn libraries and other library structures. Then we also take the user's input for deciding the number of threads that he wants to execute per node, and also the number of trees or the number of algorithms, to be precise, that every thread to execute. So there is a two-level user input that we are taking. Firstly, deciding the number of threads he wants to create, and secondly, deciding on the number of trees that every thread is going to handle. And then we split the data into test data and train data so that we can effectively train our decision tree model. And then we call the predict function of the decision tree classifier if it's a classification data set, or we call the predict function in the decision tree regressor if it's a regressive data set. So, and the final output that we get has a few changes. In the case of classification, what we do is we take the mode of all the predictions. That is, the most occurring prediction will be the final result of the classification. Whereas in the case of regression, we tend to take the mean or the average of all the numerical, or which can be integer or decimal value, and we tend to take the average of it and give the final result. And an added advantage of using this is that not only we'll get back the result, we can also get back the tree model, which was used to predict the given result. So along with the predictions, we also can get back the tree module on the ECL side once we end the embed function. So having said that, let's go have a look at our GitHub repository, where I'll be explaining the brief structure of our code and what all functionalities we have added. So this is the GitHub repository where we have uploaded our codes, which are in ECL for decision tree as well as random forest. Random forest more or less makes use of the same features as the decision tree, but random forest can be thought of as a collection of decision trees where we give the user flexibility to decide how many tree models he wants to be present inside the random forest. And if you have to put it in a simpler way, a decision tree is a special case of a random forest where the number of trees is equal to 1. So now let's just go through our decision tree module. So the first thing that we speak about in this is what are the user inputs that we need. So these are basically the lists we have created on the ECL side, which is basically class prediction holds the prediction lists for classification data sets, and rig prediction holds predictions for the regressive data sets. And these will be holding the output predictions once we end the embed and get back the predictions from the Python. And these are basically this is essentially the whole core of our project, where we have a few user inputs that such as independence and dependence, which is a part of the data set on which is independence is basically the part of the data set which is used to evaluate the prediction, that is on which the prediction is based on, and dependence are that part of the data set which will be evaluated based on the independence, and the user will accordingly select what part of the data set is the independent and what part does he want has a prediction. And then you also have n threads. N threads, it basically is used to implement the multi-threading concept of Python, where you're deciding the number of threads you're going to create, and n trees is the number of trees that each thread will be effectively handling. Now, this is our Python side. Once we have embedded into Python, it looks something like this. So as you can see, we have created multiple lists called output records fields, and we also have an independence and dependent list that we have created based on the inputs, which are independence and dependence respectively. Then we go through a for loop, which is essentially procedural and not recursive. And for every independent, we create a numerical field. And at last, you also have the data frame, which is a function that is used to create the output records. And if you can see, the last thread is basically if the number of threads that you have entered is the number of trees and the number of threads you have entered are not exactly tallying with each other. The last thread will contain any number, will basically do the operation for any number of trees that that will be left out after uniform distribution. Suppose, let's say we are executing 30 trees on 4 threads, then every thread will essentially have 7, and the last 2 trees will be executed on the last thread. So that is the function of the last thread. Just to give a brief overview, we have a decision tree where we have decision tree regression, which is a function that we use to give the prediction for a regression data set. And as I explained, the parameters remain the same: independence, dependence, n threads, and entries. This is the basic overview of the flow of the function, as you could see, which is mostly self-explanatory. We have provided documentation in necessary places if you have to go through the code so that you'll have a better understanding. Similarly, if we come down, we have another function called decision tree reg predict. Reg predict is basically used to obtain the final prediction of the data set that we have entered. And class predict is basically for the equivalent for classification data sets, where the output is obtained by taking the mean or the mode of the predictions of each decision tree rather than mean, which we take in case of regression. So the entire flow remains the same except for one place, where instead of calling a decision tree regressor, we actually call decision tree classifier on the scikit-learn library. And last, we have our class predict function, which will contain the prediction list that we have after we call the classification datasets, or and it will contain a 2D array, because there are a number of trees that we have used, and there are also a number of predictions that we have made with every tree. So accordingly, it will be a 2D data set with the number of rows equal to the number of trees and the number of columns equal to the number of predictions every tree has made. Right. Towards the last, we have one important feature that is called as the tree model, which is very essential in understanding. If you scroll, you could see the tree model. Yeah, the tree model data, the tree model function is essentially to understand how we are able to get the result. That is, what is the model of the tree and how it looks, uh, and what are the parameters it has considered, so that the users do not just have the data with them, not the just final result with them, but they also have uh, an understanding of how the decision tree was able to make the decision. So the tree model is essentially a function that returns a list of data sets, a list of trees in the form of strings. So it is essentially a 2D array, but every list is basically like an array of strings, if you could think of it like that. So this is the brief of the decision tree model. Now, let's go ahead with the random forest model. Uh, as I explained, the decision tree model is a very special case of random forests. So the explanation more or less is the same. So if you find it comfortable to use the decision tree, it's equally simple and easy to use the random forest as well. With a small change that you will have to give the input for the number of trees that you want to be evaluated by your random forests. So basically, if you see the trees that are called as end trees, is basically the parameter that the user has to decide to tell the system the number of trees that he wants to be created. The default remains 1. So if the user does not specify any value, the default is basically telling the system to go ahead with a special case of random forest, which is nothing but a decision tree. And then you have another parameter called the max depth, which is the maximum depth of the decision tree that will be created for every decision tree inside the random forest. So if you could just see the code, more or less it's the same function, except for that one additional parameter that we have used. So we have made this a public open source repository. So anyone who is interested and who needs to use this optimized code is free to use it, and also give back any feedbacks or any suggestions. Thank you. Now we shall see a brief demo of how the project actually works and the comparison between the existing and the newly modified libraries. So we have used VS Code to execute the ECL functions along with the extension of the ECL that is available in VS Code. So this is the already existing library that we are using. And basically, as you can see, we have called, this is basically for a diabetes prediction data set, which is basically like a regression data set. And we have dependents that are classified. And also we have passed parameters 15 and 69 that are basically the number of threads and the number of trees that each thread will be handling respectively. And you also have and you also have reg predict. Reg predict is basically a function that returns back the prediction once the decision tree has been formed using the decision tree reg. And reg result is used to finally obtain the result from the total list of predictions. And output is basically displaying it on the ECL watch. So just to have a brief of it, this is the modified code that we have used, as I explained in the GitHub repository. Decision tree reg, reg predict, regression result are functions that first create the decision tree based on the dependence and independence and the number of threads and the number of trees per thread. Reg predict basically gives the prediction as a list, and reg result uh, gets the final regression output by taking the mean of all the values inside the prediction. And output is basically used to display our result on the ECL watch. And if we go ahead, this is the code that we have used, and our data set, as I mentioned, is the diabetes data set. So this is the decision tree. Yeah, this is this is the function or the ML core that is already existing inside the ECL library, um, on which we have performed an optimization. So even here, we use the same data set so that we have a fair comparison. Um, and we have done the split of independence and the dependence as 0.5 and 0.5 respectively. And we are calling the regression forest, which is the equivalent of decision tree regression or in our optimized code. And finally, we are producing the same output on the ECL watch. So now if we go ahead and check our execution part, you could see this is the result that we obtained with the already existing ECL libraries, the ML core libraries. And you could see the job was named ECL test. And this is a list of predictions that we obtained. And we can see that the runtime for this on the total cluster was 21.821 seconds. Now, this is our job that we had executed with the modified machine learning library using Python. And you could see the runtime dropped drastically to 7.529, which is approximately 3 times lesser than the original runtime. So by using procedural language and an iterative loop and a very data efficient language such as Python, we were able to cut down the costs that was majorly due to the recursive nature of the loop function. And just to mention, this whole process, we tried to maintain the accuracy as close as it was to the original one. So even though there was an increase in the efficiency in terms of speed, we didn't compromise on accuracy. Now let's move ahead and have a brief discussion about the results that we obtained. So this is a brief table that we have made based on the execution of our data sets. This one is in particular for classification results. And we have tested it on two platforms, a single node, which is a personal laptop, and a multi-node, which is the 8-node HPCC cluster that we have in our university, which is managed by HPCC and RECE together. So we tested our model on two data sets for classification. One is iris valuation. The other one is restaurant quality checks. Both of them are standard data sets available on Kaggle. So we could see on the existing ML core had a runtime of 11.731, whereas our proposed embedded model was able to run it in a drastic reduction of 0.886 seconds. So that's approximately improving it by 1,324 times. The percentage improvement is 1,324. Similarly, on the multi-node, the iris valuation took 41.45 seconds. On the other hand, our proposed model took just 8.71 seconds with an improvement of 479%. As I mentioned before, the accuracy was not compromised. And even though there was a slight bit reduction from 85 to 84%, we were still able to obtain great results in terms of speed of execution. And similarly, for restaurant quality check, we have a percentage improvement of 179 for single node and 194.33 for multi-node, while we're able to maintain the same accuracy of 88%. Now, going ahead, this is a brief chart which visually describes the improvement. The blue one being the runtime for the existing library, and the red one being the runtime for our proposed model, with multi-node and single node plotted separately for the iris dataset. Now we'll move ahead to the regression dataset. Even here, we tested it on two standard datasets, being the real estate valuation and the diabetes prediction, similar to classification on single node and multi-node as well. As you can see, for real estate valuation, the runtime dropped from 11.731 seconds to 0.886 seconds, which again was around 1,324 times in improvement. And for diabetes prediction, you could see in the single node, the runtime changed from 11.032 seconds to just 0.923 seconds with an improvement of 1,195%. And the accuracy remained same, more or less, in both the cases. And you can see we have plotted a small chart to just understand how much we are able to improve the runtime and the efficiency while maintaining the same accuracy. So this was about the project that is performance optimization of the learning trees. We have successfully completed the project, and we have uploaded the code on GitHub, and along with the necessary documentation. I would like to take this opportunity to thank the college for giving us an opportunity to work on this. I would also like to extend my sincere gratitude to HPC Systems and Texas and all members who helped us throughout the project by solving our doubts and extending their support all the time. Thank you for this opportunity.